All right, folks, here we go in another video. We are still filming in front of a live studio audience. So, as promised in this video, we are going to do a rate law problem. Now, we need to remember, before we can get into a problem, we need to remember that our formula for this is the rate of formation of our products, okay, equals K times the concentration of one of our reactants. Now, last time we said the reactant of A. This time, we've actually got actual reactants. So we're going to say that this is reactant NO, that's to the X power, times the concentration of our other reactant, which is H2, to the Y power. Now, we need to figure out our orders, okay? Right now, this is listed as X and Y. We need to figure out our orders. So the way that we're going to do this is we need to find two of our experiments here where the rate of nitrogen monoxide changes, but the rate of H2 stays the same. So if we take a look right here, these two stay the same, but these two change, okay? So what we're going to do now is we are going to choose the experiment that has the faster rate or the larger number for the rate. So that's going to be experiment 4. So I'm going to do experiment 4 over experiment 3. Now, right now, I've written 4/3. I want to tell you right now, 4/3 means absolutely nothing, okay? The only reason that we have this written is so that we can remember that this is trial 4, okay? This is trial 4 or experiment 4 over trial 3. So what we're going to do is we're going to write that same formula that we did a second ago. The rate of trial 4, which is 1.2, times 10 to the negative 4 equals K, which is unknown, times the concentration of nitrogen monoxide, which is 0.20, to the X power, times the concentration of H2, which is 0.60, to the Y. Okay, that's everything for trial 4. Now we're going to do the same thing for trial 3. We're going to do all of this over the same thing for trial 3. Trial 3 is 0.30 times 10 to the negative 4 equals K times 0.10 is the concentration of NO to the X times 0.60 to the Y. So now let's take a look and see what all can we cancel. We can cancel K. We can cancel 0.60 to the Y. Okay? So what we need to do now is we need to do some math. Okay? So I'm going to do 1.2 second E negative 4 divided by 0.30 second E negative 4 and see what I get. I get 4. Okay? Now I need to combine 0.20 over 0.10 to the X. I can actually just go ahead and combine these. So I can do 0.20 divided by 0.10 is 2, and then we can bring down the to the X power. So what I have is 4 equals 2 to the X power. Now, a lot of y'all can probably see right now what X equals. The reason that you can see what X equals is because we're using easy numbers, okay? Most of y'all can probably say, oh, I know what, 2 squared is 4, so obviously that's my answer. Now, if this were like 18.3 and this were 3.682, then you need to know what to do from there. So what we're going to do for all of those of y'all who are taking Algebra 2, you've seen this before. We're going to take the log of both sides, okay? When we take the log of both sides, what I can do is I can take this X and I can swing it down in front of the logarithm. So now what I have is log 4 equals X log 2. Well, how do we get X by itself? Of course, we're going to divide both sides by log 2. Okay, log 2 cancels, and so I see now that X equals the log of 4, close parentheses, divided by the log of 2, close parentheses, enter. And I get that x equals 2. So here's what we would say. We would say that nitrogen monoxide, the concentration of nitrogen monoxide is second order with respect to, well, nitrogen monoxide. We say this reaction is second order with respect to nitrogen monoxide. So I guess we wouldn't say nitrogen monoxide is. We would just say that this reaction is second order with respect to nitrogen monoxide. Well, you're probably now asking, well, what do we do for H2? Guess what? We're gonna do the same exact thing. Okay, we're going to find two trials where nitrogen monoxide stays the same. Oh, how about right here? And H2 changes. How about right here? So now I'm doing trial 2 over trial 1. T2 over T1. Now, does T2 and T1 mean anything? Absolutely not. Okay, we're just going to circle these and we're going to say, that's going to be our reminder for what we're doing. So I know that trial 2's rate is 3.6 times 10 to the negative 4. And that equals the first off, it's K, times the concentration of nitrogen monoxide, which is 0.60. What am I going to say to the x? No, actually, I can just say squared, right? Because we already found out that x equals 2, so I can just put the squared in there. Times the concentration of H2, which is 0.20, to the y. Okay? We're going to do that over everything for trial 1. Okay? So trial 1 is, the rate is 1.8 times 10 to the negative 4. And that's times K times 0.60 squared and 0.10 to the y. Okay? And so now we're going to cancel where we can. So let me choose a different color so we can cancel. K's cancel. 0.60 squared cancels. And now I have 0.20 to the y over 0.10 to the y, which of course is just going to be 2 to the y. And that equals 3.6 times 10 to the negative 4 divided by 1.8 times 10 to the negative 4 is 2. Now, a lot of y'all, once again, you can probably see what the answer is going to be here, but nonetheless, we're going to take the log of both sides. So I'm going to have log of 2 equals y, because I'm going to bring that down when I put log in front, y log 2. Okay, divide both sides by the log of 2. Divide by the log of 2. Cancel, cancel. And I get that y equals 1. So we would say that this reaction is first order with respect to the concentration of H2. That's how you do it, my friends. That is how you do it. So now what's our overall order of our reaction? Well, we know that nitrogen monoxide, if we go back up here, we know that nitrogen monoxide was second order with respect to NO. We know that our reaction is first order with respect to H2. So what we're going to do is we're going to say that the overall order is the order of the first one plus the order of the second one. So the overall order of the reaction is third order. Okay? Now, if we're going to write the temperature-independent rate law expression, that means that we're not going to solve for K. Okay? We're just going to leave K as K. So I would say that the temperature-independent rate law expression is just going to be this. What the expression is it's basically a formula that we can plug things into. So the temperature-independent rate law expression is going to be as follows. The rate of this reaction, which we can calculate, the rate equals K times the concentration of nitrogen monoxide, whatever it may be, squared, times the concentration of H2, whatever it may be, to the first power. Okay, that's my temperature independent rate law expression. Now, you're probably noticing, well, if there's a temperature-independent rate law expression, I bet there's a temperature-dependent rate law expression. The way you find that out is it's the same exact thing, okay? Temperature-dependent is the same exact thing, but instead of rate equals K times the concentration of NO squared times the concentration of H2 to the 1, now we have to solve for K. How do I solve for K? Guess what I'm going to do? I'm going to come back up here, okay? We'll come back up here, and I'm going to find one trial that I can use, okay? I'm going to find one trial that I can use, and I'm going to plug everything in to my temperature-independent rate law expression. So let's use this last one. 0.20, 0.60, and 1.2 times 10 to the negative 4 is my rate. I hope I can remember all that. 1.2 times 10 to the negative 4, 0.0020. You know what? I've been doing... Well, luckily, we got the same answers, but yeah, I'm so sorry. It's actually 0.0020 and 0.0060. Whatevs. Y'all know what's up. All right, so the rate is 1.2 times 10 to the negative 4 equals K times 0.0020, was it? Yes? Okay, good. 0.0020 to the second power times 0.0060 to the first power. Does this look like something we can solve? Guess what? We can, okay? So I'm going to divide both sides by 0.0020 squared times 0.0060 to the 1 is just that, okay? So we're going to divide this by 0.0020 squared times 0.0060, okay? And let's see what we get, okay? So I've got 1.2 second E negative 4 divided by, open parentheses, 0.0020 squared, where are you? There it is, times 0.0060, close parentheses, Shazam. K equals 5,000. K equals 5,000. What's my units? Okay, remember way back when in the first video we talked about how the unit for K is time to the negative 1 times molarity to the negative overall order minus 1. Well, what was our time? If we go back up to our chart here, I see that we're dealing with molarity per minute, okay? So that means that my time unit is minutes. Okay, so this K is going to be 5,000 minutes to the negative 1 times the molarity to the negative overall order minus 1. Well, my overall order was 3. 3 minus 1 is 2. So guess what? Here, my friends, is my value for K. Well, we're going to finish out the temperature dependent rate law expression by plugging in this number for K. All right, we're just going to plug that in right there. 5,000. Shazam. There, this is my temperature dependent rate law expression. Now, really what I need to do as well is I need to determine the rate of this temperature for the following concentration with units. And so I need to plug 0.0019 in right there. And I need to plug this number in right there. And I need to do the math, okay? But I'm at 13 minutes and 38 seconds, so I do not have time for that. So I'm going to let you do that on your own. I'm going to trust that you can plug that into your calculator. And you solve for the rate, and that's it, my friends. That is it. We're going to do more problems like this in class. Have a wonderful day, and thank you very much to second period. Woo! All right, and we are